Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome back to Week 5, Lecture 2 of Dynamic Atomic Force Microscopy Methods. We have been talking in the last class about electrostatic force microscopy. In particular, in the last class, we had focused on understanding the origin of work function of conductors and how, when a conducting tip is brought close to a conducting sample, an electric field develops between the two, which, if one tries to null with the help of an external voltage bias, that leads to a very interesting way to actually measure the work function differences between different conducting surfaces. We also talked about the fact that the Kelvin force probe, or the Kelvin probe force method, is microscopy method, is actually based on an older version where a mechanically oscillating system was used to actually map out the work function of the surface that you want to measure. And then we did talk about the Kelvin probe force microscopy idea, whereby a cantilever is subject to two different excitations. One is a mechanical excitation, exciting the cantilever at its resonance, mechanical resonance frequency. And then there is an electrical excitation signal, which can be applied either to the sample or to the cantilever. But the frequency of that second excitation frequency, the electrical frequency, is usually much lower than the mechanical one. But the cantilever responds to electrostatic forces that arise as a result of that excitation. But the response, the cantilever responds at two frequencies in response to the electrical excitation. It responds at omega elec and 2 omega elec. We talked about the fact that by nulling the omega elec channel by applying a DC bias voltage, we're effectively measuring the contact potential difference between the tip and the sample. And the 2 omega elec signal is really giving us a magnitude of the gradient, the vertical gradient of the capacitance formed between the cantilever and the sample. As a result, what's really nice about Kelvin probe force microscopy is that we have different channels for topography. The topography is based on normal feedback, for example, in tapping mode, or you can use frequency modulation for it, based on the response of the cantilever at the mechanical excitation frequency. At the same time, by nulling the signal cantilever vibration at omega elec, we're actually mapping the contact potential difference in one channel. There's a third channel you can get out if you have a third lock-in amplifier, which is then going to give you the DC-DZ, or the gradient, vertical gradient of the capacitance. And as was discussed in the, as was mentioned in the last lecture and, written out in the appendix of the last lecture, the gradient of the capacitance actually is the one that contains information on things such as the dielectric constant, in case you're dealing with a dielectric on a conductor, or the thickness of the dielectric, and so on. So these are some very nice features of Kelvin probe force microscopy, in that it can separate these channels very nicely. We also talked about the fact that contact potential difference, at its fundamental, is basically about applying a bias voltage to nullify the electric field. As one nullifies the electric field, one ensures there's very little current transport going on between the tip and the sample, which is useful for a number of reasons. But the second important thing about nulling the electric field is that the contact potential difference that we measure using the technique can be related to the work function if the tip and sample are properly prepared. If both of them are conducting without contaminants, then it makes sense. On the other hand, if you've got a complex material you're trying to image, where parts of it are conducting, parts are not conducting, there might be contaminants on some of the conducting parts. The contact potential difference measures a mix of properties. It ends up measuring some sort of combination of forces that might arise, for example, due to charge, trapped charges due to the presence of a dielectric layer that might change the capacitance and so on. So in order to ascribe contact potential difference to a physical property like work function requires very careful preparation of surfaces. In the same sense, if CPD were used to estimate, for example, the dielectric constant of a dielectric medium on a surface, we again need to make things sure that certain other things are kept constant, for example, the thickness of a film and so on. So what we're going to talk about today is we'll move ahead from Kelvin probe force microscopy and speak about some of the methods that are used for measuring electrostatic forces, and then we'll talk about certain examples, some examples of results, kind of things you can do with Kelvin probe force microscopy, and we'll end up with a discussion on what needs to be done to make Kelvin probe force microscopy more quantitative, or in general, electrostatic force measurements more quantitative. So we're going to start with a quick discussion of two other commonly used methods for doing electrostatic force microscopy. The first is called one-pass or single-pass electrostatic force microscopy, as the schematic of which is shown on the top left. In this technique, what one does is one applies a mechanical excitation signal and one applies the electrical excitation signal. The mechanical excitation, the response to the cantilever, the mechanical excitation is used to follow the topography of the sample as shown. The electrostatic force that's applied can be DC or AC. You can choose the frequency at which you do it. But basically, the idea is while you're tapping on the sample and scanning the topography, you simultaneously measure the response of the cantilever at omega elec. That, as I said, you could have omega elec be 0, in which case you're doing DC single-pass electrostatic force microscopy, or it could be at a low frequency, 5 kilohertz, 10 kilohertz, like we've discussed before. The bottom line is that the response of the cantilever at omega elec, which would be the amplitude and phase, would be the channels that give us contrast regarding local electrostatic properties and local electrostatic forces. The criticism or disadvantage of this technique is the fact that as one is scanning the sample, we have the electrostatic forces active. We have possibly DC bias, we possibly have AC bias on the sample, which means that as long as there are electrostatic forces between the tip and the sample as you're scanning, what it means is that the topography that you're actually scanning may not be the real topography of the sample, that it may be influenced by large electrostatic forces that might occur at certain points of the sample. So, for example, if you're scanning over a topography and there's a patch of, very strong patch of charges on a dielectric sample, which causes large electrostatic forces, which actually detunes the cantilever resonance from, its natural frequency. In that case, the controller would see a reduction in amplitude, not because the topography is increased, but rather because there's just a lot of charge on the surface that force the cantilever amplitude to drop by the detuning of the resonance frequency. And then the controller would respond to that by moving the base of the cantilever up so that you have more amplitude. And so you could have, hypothetically, a situation where you have a flat surface but just a large charge density, large electrostatic forces in a small part of it, which would be misinterpreted by the topography image. Which is why the two-pass EFM method is considered useful because it tends to separate the effect of large electrostatic forces on the topography channel. How the two-pass EFM works is basically you turn off any voltage applied, any electrical signal to the cantilever, image the topography of a sample in the absence of any applied voltages, and we would regard that topography as being the real topography of the sample. And then once that topography is recorded, once you do a line scan, in the same line, or before moving to the next line scan, you offset the Z position of the cantilever. You move it up by a certain offset distance, which is chosen by the user. User can choose that distance. And now, the cantilever is made to go over the same profile that's just been measured, the same topography profile, in an open loop fashion without any feedback turned on. So in other words, once the topography of the sample has been figured out, you do this offset, and then you drive the cantilever to resonance, move the base of the cantilever up and down to follow the topography that has been measured in the previous scan, but without any feedback on the amplitude and phase of the cantilever as it scans over. And while that is happening, all you have to do is to record the response of the cantilever, the amplitude and phase at the electrical excitation frequency. In this case, the material property channels or the local electrostatic property channels would be the amplitude and phase at omega elec, but at a certain offset distance, and you tend to reduce the effect of local high electrostatic forces in the measurement of topography. The downside of this technique is that even this technique does not really ensure that topography does not contain artifacts due to electrostatics. And the reason for it is because, as we have discussed before, there's always going to be some electrostatic field even if you don't apply a DC voltage. And so really the best way to get a clean topography channel is likely to be to use the Kelvin probe force microscopy method, where point by point in the sample you null the electric field between the tip and the sample, so that what you truly pick up is going to be the topography of the sample. Nonetheless, these are two techniques that are often used in the literature. The main difference between single pass EFM and KPFM is in single pass EFM, we're not doing a feedback to null the response of the cantilever at omega elec. So let's go over some examples of some kind of problems that you can look at using some of these techniques. The first I'm going to talk to you about is a technique that's not about scanning. It's a very simple idea of implementing EFM without scanning, which is if you position the tip over a sample and you excite it at omega elec, but you change the bias voltage applied to the cantilever or to the sample. What one would do in this case, in this particular case, we're changing the bias voltage applied to the tip. And all one tries to study is how does the response of the cantilever at omega elec change as a function of the applied bias voltage to the tip over a particular sample. In this case, it's a gold sample. And so it's really the output of the EFM lock-in, which is at omega elec, that's being plotted along the y-axis in this case, and the tip bias voltage is plotted at the bottom. What one notices very interestingly is that you get this characteristic V-shaped curve, which proves that when the sample is set at a certain voltage, V sub S, there is a certain tip bias voltage at which the omega elec, or the output of the cantilever at the electrical excitation frequency, goes to 0, which is the bottom of the V, right? So at that tip bias voltage, the response at omega elec becomes 0 and vanishes. You have effectively nulled the electric field between the tip and the sample at that point. And just to test that you're getting the right position for the nulling, right contact potential difference, you can play around in this experiment as shown here by actually applying a bias voltage to the sample. And what you see is how these V-shaped curves of response at omega elec versus V-tip change as the bias voltage is changed, suggesting that for every different bias voltage you actually need to move, you have to apply a different tip bias voltage to nullify the electric field between the tip and the sample. Why it's a V-shaped, it should be pretty obvious. If you go back to the expression for electrostatic force on the cantilever at omega elec, you will recall that it's proportional to voltage difference the whole squared, which means that whether the V-tip is more than the V-sample or V-tip is less than the V-sample, you're going to get the same electrostatic force. So you get a quadratic-like shape, which is basically a V-shaped response curve. here I'm showing you another interesting example of how one might actually use a scanning KPFM measurement for looking at some interesting samples. Again, the work I showed you in the previous slide is out of Ron Reifenberger's group in the Department of Physics here at Purdue. And what I'm showing you again is of a student in his group, Brian Walsh, from his master's thesis some time ago at Purdue. What is shown here is a very interesting sample where there's a multi-walled carbon nanotube laying on a glass substrate, and then titanium gold pads have been evaporated on either side of it. So in effect, you have a multi-walled carbon nanotube that's been coated by a cladding, a gold titanium cladding on either side. And the intent of this experiment was to sort of measure, using Kelvin probe force microscopy, the transport properties by applying a voltage, a source drain voltage across the carbon nanotube to look at the electronic transport properties within the tube using Kelvin probe force microscopy. That was the intent. But what was interesting about this is that in this particular case, as you notice from the tapping mode topography image, that the multi-walled carbon nanotube was broke at a certain point indicated by the yellow circle. Nonetheless, of the two gold pads, a positive voltage is applied to the pad on the left, and the contact potential is mapped out using Kelvin probe force microscopy as shown on the image on the top right. What one sees is a very interesting picture. By the way, the dashed yellow lines, vertical lines, indicate the positions where the gold electrodes end and the glass begins. There are two important things one would notice from here. The first is that what we would expect to see is that you would expect to see a large contact potential voltage on the left electrode, and then as soon as you get on the gold, there should be a sharp drop-off in the contact potential as you move across. The drop-off is not sharp, as you can see that the bright region of the contact potential difference extends beyond the first vertical yellow dashed line quite a ways. The reason this happens goes back to an interesting complicating fact that we'll talk about in the next few slides, and it has to do with the fact that even though the cantilever's away from the edge of the electrode, there's still a very significant part of the capacitance. There's a lot of electric field lines that still go from the cantilever to the electrode. So just because you're not sitting on top of the electrode doesn't mean that you don't experience electrostatic forces coming from that electrode. So there's a very big convolution effect that happens when you deal with electrostatic force microscopy with large electrodes and large cantilevers. We'll talk about that in a bit. So it's very important then to line up those yellow lines to tell us, based on the topography, to tell us where the electrodes end and where the glass begins. Otherwise, we won't know where that happens. So as you look through this, you find the contact potential difference has been plotted in the bottom right across the green line, which follows the multi-walled carbon nanotube, and across the red line, which basically goes off the electrodes onto the glass and back onto the electrode on the right. What one sees here, very interestingly, is that on the glass, the red curve of the contact potential difference shows a gradual decrease and then going down to a constant value on the right-hand side as you approach the grounded electrode on the right. On the other hand, the multi-walled carbon nanotube, being conducting in nature, supports a nearly constant contact potential difference until you reach the break point, beyond which the carbon nanotube to the right is not electrically connected to the carbon nanotube on the left, and its contact potential difference, the broken parts, goes down to that of the substrate, the glass substrate. So there's some interesting measurements like this that can be made using Kelvin probe force microscopy. However, I'd like to go back a little bit and pose the following question. At the end of the day, what we do in Kelvin probe force microscopy is we measure two channels of information. We measure the contact potential difference on one hand, and if you have a third lock-in amplifier, you can pick up the gradient of the capacitance DC-DC. What one is trying to do, or very often is interested in Kelvin probe force microscopy is quantitative measurements of physical properties of the material, electronic properties of the material you're scanning, which requires us to take observables such as contact potential difference and convert them into things like the work function. And I've already talked to you about what needs to be done to get there. Another interesting aspect is the use of, or the measured value of dc/dz, the gradient of capacitance, and how to use it for mapping, let's say, the local dielectric constant, or the local thickness of the dielectric film, and so on. So the key point is that in all these cases, we're measuring and nulling forces, and we want to relate what it takes to null those forces, or what it takes to relate those measured forces to local electronic properties. That mapping is going to require us to have a good model that connects the tip geometry to the local properties that we're interested in studying. And so this has been of interest from a very, very long time in the literature. And from the early days, it was recognized that electrostatic forces being long-range forces, the force between the tip and the sample is not going to be confined to the very end of the tip. We have to start worrying about, for example, the edges of the tip, and so on. And so this is one of the earlier works that came out of France and studied systematically through computational techniques how, if you took a general tip that is shown here with a certain cone angle theta and a tip radius r, and on the right is shown the equipotential line. So when you apply a voltage to this tip, how do the equipotential lines change and separate? And you can kind of begin to see from this that when you have an object that you're trying to image with this tip, there's going to be a very strong convolution between the tip geometry and the iso-equipotential lines that come out from it. It's going to be a very close relation between tip geometry and the feature you're trying to image in terms of creating convolution in the AFM channels. So this work, based on these computational techniques, concluded that the model you need to use to connect, or to the model for the capacitance and electrostatic force that you need to use to convert the measured data into local numbers can be well approximated by a sphere-plane interaction if you're dealing with conducting tips and conducting samples, as long as the tip is very close to the sample. Very close meaning much closer than the tip radius itself. On the other hand, when the tip is a little further away from the sample, then the best model that captures the electrostatic field and the capacitance is actually one of a cone. But you need to model it as a cone or a straight line of charges, and there's an analytical expression for it, which very well approximates the capacitance that forms between the tip and the sample and the resulting forces. And finally, if the cantilever is really far away from the sample, you have to get rid of that as well. You cannot rely on the cone model as well. The key point out of this was that the correct expression to use depends on the tip-sample gap being tested. Later on, and I'll go over to the board to illustrate this point, it was realized early on that if you have a cantilever like this over a sample, a conducting cantilever, the electric field lines and the capacitance that's formed between the cantilever and the sample can be broken up into three different parts. The first is you can imagine the field lines coming out of the spherical tip of the cantilever, and this plays a major role in the overall capacitance because it's the part that's closest to the sample and it's the sharpest part, so the electric field lines are very concentrated. So the tip contributes a lot to the overall capacitance, but so does the conical side face, and not surprisingly, also the entire cantilever provides a local capacitance, a contribution to the local capacitance. The key question is, which one of these capacitance, these three capacitance, dominates? And the answer to that question was answered actually by this work coming out of Jaime Colchera's group, as shown in this slide, which shows that they derive expressions basically for the electrostatic interaction forces, and show that in reality you have to take all three pieces into account. You have to use an expression for the peripheral tip radius, for the cone, and for the cantilever, and the three of them are in general all active at very short distances and gaps. Certainly the sphere is what dominates, but in general situations you need to take all three into account. Other analytical approaches or computational approaches have included advancements in coming up with good accurate models for capacitance and electrostatic forces between these tips, and samples where now you have dielectrics on them, as shown by the second article in here. Most recently, I would say that there's been a trend in the literature on trying to realize that maybe analytical models that connect tip geometry to local properties may not be the most accurate way to go. And in recent years, there's been a trend towards the use of finite element methods to really understand how the capacitances form and how they're related to local properties in a substrate. So these are some of the outlying issues that I'd like to bring to your attention, regarding electrostatic force microscopy. And from the next lecture onwards, we'll be talking briefly about magnetic force microscopy, and then we'll talk about AFM and liquids. Thank you.